So let's continue our discussion for the next topic called identity of function. Identity function is something which is defined on the same set A. The identity function f between the set A and itself A is such that each element is actually associated to the same element in the set A. Okay, so let us understand by means of a small example. Suppose I have a function f defined on the set A to A such that for all x belongs to A, fx is equal to x. Right? So that means if I take two sets A, both are the domain and codomain set A to A, suppose it has four elements A, B, C, D. Here also there are four elements A, B, C, D. So A is associated to A, B is associated to B, C is associated to C, and D is associated to D. Then it is known as a identity function. Identity function on a set A is generally denoted by IA. Identity function on a other set B is denoted by IB, like that. Clear? Our next topic is called composition of function. What does it mean? It means that suppose I have two functions. One function is f, which is defined on two sets A and B, and I have another function g, which is defined on two sets C and D. Now let's see whether you can compose these two functions, okay, f and g, and whether you can find another function out of f and g. That is the discussion of the topic, composition of function. Suppose I have two functions. One is f, it is defined between the sets A and B, and I have another function g defined between the sets C and D. Okay, let's describe it pictorially. So this is the set A, this is the set B, this is the set C, and this is the set D. So what is our function defined? Here is a function defined from A to B by means of f, and here is a function defined between C to D is the by means of the function g. Correct. Now we are thinking about composing these two functions f and g, and that is only possible if the range set of f, range set of the set A by means of that function A is a subset of the domain set of the function G. Why? So what is the condition? After that I will come why. That means the range set of the domain set A for the function f is denoted by fa, right? And fa has to be a subset of C. That is the domain set of the other function G. Then, if it is possible, I'll come after some time why it is so. Then it is possible to have a function G which will map an element A to the element in D. Right? Let us take that example here. Suppose this is the element X in the set A. This is the element Y in the set B. This is the element Z in the set C. And this is the element T in the set D. So what we can write? We can write Y equal to Fx. And we can write T equal to Zz. Very simple. Now the composition is only possible if this element Y is also belongs to the element C. Sorry. The element Y belongs to the set C. Otherwise, I cannot have as association of that element which is the image of the element X in the set B with D. So that's why that fa, the domain, that is the range set of the set A, should be a subset of the set C, which is the domain of the function G. So then what will happen if it is so? So now if fa is a subset of C, then what we can find? We can find Y and Z. We can find that Y, the value of Y in Z. That means we can think of that this is the FA, right? This is the set FA. Alright, this is the set FA. Now, the point is that composition function. Suppose this is the composition. This is my mapping from F. This is G, and this is composition function. Suppose H. So what is H? H is nothing but a mapping from A to D. Yes, from A to D. Such that T is equal to H of X right? T equal to H of X, right? Now what is T? T is nothing but G of Z. T is nothing but G of Z. And what is Z? What is Z? Z is nothing but, in this case, as the moment FA is a subset of C, then you can find that Z and Y are in the same set, correct? Then you can find that Z and Y are the same set, so Y is equal to Fx. Y is equal to Fx. Okay? Now we can make a restricted version of this one, of composition function. Restricted, the moment we say FA is a subset of C. So, what we are having here is that I have the set A, then the set B, okay, and then the set C. So there is a mapping from or function from A to B. Suppose it is F A to B, and there is a mapping from B to C. So suppose G from B to C. So please remember one thing, here I explain the concept that why this statement is important. If A is a subset of C, this condition is important to have a composition function, right? The moment, again I repeat, the moment Fa is a subset of C, we can tell, yes, this is the Fa, the B, not exactly the set B, the subset of B, so that will be the subset of that, the domain set of the other function G, so we define as a B, okay, which will cover the entire case. So what we see here, X is an element, we get an element Y by means of the function F, and for the element Y in the set B, we get an element Z in the set C by means of the function G. So this is the function F, this is the function G. So what we see, here you see is that Y equal to Fx, and we see Z equal to G of Y. The moment Z equal to G of Y, we can say Z equal to G of, what is Y? Y is nothing but f of x. So we can write f of x. So we see that Z and X are related, right? So Z and X are related. Z and X are related by means of a function G of fx. We generally denote it as, this implies Z equal to G naught fx. So G naught f is nothing but this function, so that is G naught f. Correct? So this is called composition of function. G naught fx. So our general terminology is like this: G naught fx is equal to G of fx, and f naught gx is equal to f of gx. Later we'll see, while we discuss some advanced topics on function in future, we'll see that g naught f and f naught g is not necessarily they has to be equal. Okay, here we just conclude this thing generally. G naught f is not equal to f naught g. We'll see it later why it is so. I hope you got a good amount of understanding about the composition of function. That we just first discussed about two discrete function f and g, where the codomain set of f is different than the domain set of g, domain set of g. Then later we conclude why some kind of relationship should be there between C and the A. Okay, what is that? The range set of A should have to be a subset of the domain set of the other function g. Then only we can think about composition of function. If A is not a subset of C, there is no question that we can think about composition of function. Composition of function in that case is not possible. It is only possible if this condition satisfies. Then we come back to the more proper way of defining a composition of function. There are three sets A, B, C. Instead of considering four sets A, B, C, D, the moment we find that B and C are related by means of this, if A is a subset of C, we just made three sets A, B, C, and the function f is defined between the set A and B, and the function g is defined between the set B and C. That means what? The codomain set of the function f becomes the domain set of the function g. Then you find that there is a possible to define a composition of function g naught f, composite function also known as, which satisfies this one. Okay. Uh, so what I suggest you, just spend a couple of minutes to understand this thing, and we'll then proceed further for our next topic of discussion. Alright, so our next topic, we are going to discuss about the few properties of composition of function. Okay, before that, we can have a small example to look into it on the composition of function. Suppose we have two functions f defined from a real number to real number, and g also defined from a real number to real number. And what is fx? Fx is defined as x plus 5, and gx is defined as, suppose, e power x. Now let's see what will be our g naught fx. G naught fx will be, according to the understanding we saw, g of fx. G of fx. So that is equal to g of, what is fx? Fx is x plus 5. Now what is gx? Is e power x. So g of x plus 5 will be e power x plus 5. Now let's see what is f naught gx. F naught gx is equal to f of gx, and f of, what is gx? gx is e power x. And fx is x power 5, so f of e power x is equal to e power x plus 5. So what you see, g naught fx is equal to e power x plus 5. But where you see f naught gx is e power x plus the number 5. So we see g naught fx is not equal to f naught gx like this. But you can find the cases also where g naught fx is equal to f naught gx. Okay, you can try it out and let me know later. Now, next topic is, as I said, some properties of composition of function. We can discuss it here as well. Okay. Let this portion be still there. In case you want to have a look into it, you can look into it. Suppose I have two functions, f a to b and g b to c. The point is that if the function g naught f is to be defined, both f and g has to be defined. Okay, number one. The composition function, number one, is that g naught f is a function from a to c to be defined f and g has to be defined. Number two. Okay. If both f and g are injective, then g naught f is injective. Okay. If both f and g are injective, that implies g naught f is injective. the converse of this statement is not necessarily true. What does it mean? If G naught F is injective, that doesn't mean always I need to have both F and G as injective. If it can be, but it may be possible that F is injective but G is not. Then also it is possible G naught F to be injective. So what is that one? Third one is that if G naught F is injective, this implies F is injective and G may or may not be injective. So that is called, necessary and sufficient condition in mathematical logic. We will discuss later. So I repeat the statement because it is a little interesting to most of you. That if both F and G are injective, then G naught F is injective. But the converse is not true exactly in the same manner. That means what? If G naught F is injective, then the condition should be that then what you can conclude is that F is injective and G may be or may not be injective. That means it may be possible that G is not injective, F is injective, but G naught F is injective. It is possible. Similarly, the other case, if both F and G are surjective, this implies G naught F is surjective. Again, the converse is not true. That means if G naught F is surjective, that doesn't mean always that I must have to have F and G as surjective. There, G has to be surjective. F may or may not be surjective, right? Sure. If G naught F is surjective, this implies G is surjective and F may or may not be surjective. If both F and G are bijective, obviously G naught F is bijective, right? Because it is both injective and surjective, and the other way. If G naught F is bijective, that means both F and G are bijective. Clear? So what I suggest you, just have a detailed look into it, consume the statements. In case of any doubt, please do let me know before we proceed for the next topic, that is called inverse of a function.